Hello everyone. So in this pre-lecture tutorial we're going to build on what we've been learning in Chapter 6. If you recall, basically we've been working on naming binary ionic compounds, which are compounds made up of two ions that have been joined together to give us a compound. But the compounds that we've been working with so far have consisted of monoatomic ions, or ions made of one atom only. Now we're going to start to consider polyatomic ions. Now, polyatomic ions are formed from more than one atom. Okay, now a large portion of these polyatomic ions are what we call oxyanions, which basically are negatively charged. And they contain oxygen. Now, there are those polyatomic ions that are not oxyanions, and we'll discuss those briefly in this tutorial and obviously discuss them in greater detail in class. So, when it comes to naming these polyatomic ions, it can be a little bit confusing because there are a fair amount of these polyatomic ions and they're named similarly, and basically because of that, it can be a little bit confusing. The formulas are also somewhat similar, but I'm going to give you some tips and some pointers, and hopefully working together on this pre-lecture tutorial and also working to reinforce concepts in class, it won't prove to be too difficult. So for me, I find it's helpful if you learn the following ions by heart and then work from there. So the majority of these polyatomic ions will have a name that ends in the prefix ATE. So for example, ions like nitrate, also sulfate, phosphate, and also chlorate. Okay, now I'm actually going to draw a vertical line. Okay, and we'll consider chlorate a little bit later in the tutorial, but for now, let's work with the other three that I mentioned earlier. Now, the formula for nitrate ion is NO3-. Now, sulfate would be SO4-, and phosphate is PO4-. Now, it turns out that each of these three ions has another related ion that's very similar to it in terms of its formula. And each of these ions that I'm speaking of actually has one less oxygen than the formulas that I've written here. So, for example, nitrate represents just one potential polyatomic ion formed between nitrogen and oxygen. There's another that has the formula NO2-. Now, if you notice, basically there are two oxygens in NO2- and three oxygens in NO3-. When it comes to naming these polyatomic ions, the ion that has one oxygen less than the ion that ends in the ATE suffix gets a very similar name, except it's going to end in an ITE suffix instead. So I would name NO2- nitrite, since it has one less oxygen than nitrate. Similarly, sulfate has a related ion, another potential polyatomic ion that would form between sulfur and oxygen, but instead of having 4 oxygen atoms, it's going to have 3, one less oxygen than the sulfate. And so, because it has one less oxygen than sulfate, we would use this same ITE suffix, and we would call this polyatomic ion sulfite instead of sulfate. Similarly with phosphate, there's also a second potential polyatomic ion that would form between phosphorus and oxygen, except its formula is PO3, 3 minus. And so we would call that ion phosphite. Okay, now if we take that same idea and actually apply it to chlorate, then we will get another possible ion that would form between chlorine and oxygen aside from chlorate. Chlorate's formula is ClO3 minus. If I take away one oxygen from the formula for the chlorate ion, I end up with ClO2 minus. And so the formula that is represented by ClO2 minus would be named the chlorite ion. But when it comes to halogens, they behave differently than, say, nitrogen, sulfur, and phosphorus. They don't just form two potential different oxyanions, they can form 4. And so there is potentially another ion that has one less oxygen than ClO2 minus. So that formula would be ClO minus. And we call that ion the hypochlorite ion, where this prefix hypo means less. And so basically, since there's one less oxygen in ClO minus as compared to ClO2 minus, we call that the hypochlorite ion. Now, on the other end of this series, there's also another potential polyatomic ion or oxyanion that forms between chlorine and oxygen. It has one more oxygen than ClO3 minus, and so its formula would be ClO4 minus. That ion would be named perchlorate, where this per comes from the prefix hyper, which means too much in scientific terminology. So basically, that oxyanion that has too much oxygen compared to the chlorate, or one more oxygen compared to the chlorate, that would be called the perchlorate ion, okay, because of this prefix hyper. Now, as it turns out, there's also another oxyanion that's similar to nitrate, sulfate, and phosphate. It has this formula, right? And since it's the oxyanion that forms between carbon and oxygen, basically we call that the carbonate ion. Okay, we don't necessarily see a carbonate ion at all when we deal with naming common binary ionic compounds, so basically we do see carbonate. We will be talking about derivatives of the carbonate ion in class in greater detail, and there are also some exceptions. To naming polyatomic anions, or polyatomic ions in general, that don't necessarily follow this system. Like, for example, there's this ion OH minus. That's the hydroxide ion. There's also Cn minus. That's the cyanide ion. And then there's also, and this one's a little bit more complex, it's C2H3O2 minus. We call that acetate. And there is actually one polyatomic ion that's common that has a positive charge, and that's the ammonium ion. Now, as it turns out, these are not the only polyatomic ions that we'll encounter, but at least for now, it's a good starting point from which to now try and apply and name some compounds and write some formulas for some compounds that contain polyatomic ions. So, for example, suppose that I wanted to write the formula for calcium carbonate. What I would need to do is essentially what we've been doing when we've been naming binary ionic compounds before, and that's write the formula for each ion and then put them together and balance the charges. So, again, based on our work from last week, I should be able to write the formula for calcium as calcium 2+. We just learned that carbonate has this formula, so that means CO3 2-. We're going to cross the charges. Okay, and that gives me Ca2. And since I want this subscript 2 to apply to the entire carbonate ion, I would enclose it in parentheses and put the subscript just outside in the lower right-hand side. Now, if you notice, there is a common factor of 2 among both of those subscripts. And so, because of what we learned last week as well, I can cancel out this factor of 2, and that makes my formula CaCO3 for calcium carbonate. Magnesium, right? Based on last week's work, we should know that its formula for its ion, for the magnesium cation, is Mg2+, and we just learned that nitrate has this formula, NO3-. So once again, I'm going to take these charges and I'm going to cross them over to create the subscripts for my formula. So it would be Mg, and then NO3, but I want 2 of them, and so I need to enclose the nitrate ion in parentheses and write a 2 just outside on the lower right-hand side. And that would make the formula for magnesium nitrate, Mg, parentheses, NO3, 2. Now let's look at aluminum sulfate. Again, based on last week's work on monoatomic ions, we should be able to tell that the formula for aluminum cation is Al3+. And again, we just learned in the previous slide that sulfate is SO4, 2-. I'm going to take my charges and cross them over. And so I'm going to get Al2 and then SO4, but I want 3 of them. And so I'm going to put a parentheses around the sulfate ion and put a 3 right outside the parentheses. All right, so that's how I would write these particular formulas for these compounds. Let's go backwards now, if you will. All right, I want to name these compounds. Okay, a good first step here is to uncross the charges so that you can actually see, or uncross the subscripts, so you can actually see the charges for the individual ions. So I'm going to take this 3 and cross it and bring it up. Take that 2, cross it and bring it up. It gives me Mg2+ and PO4 3-. We know Mg2+ is the magnesium cation, and PO4 3- was phosphate. So that would be magnesium phosphate. Now again, keep in mind, magnesium is a main group metal, and so as a result, I don't have to worry about the Roman numerals because magnesium always forms a 2+ cation. Let's work with the next one. All right, I'm going to take this 3 and bring it up and cross it. That means that my charge for the aluminum is Al3+. Notice that the subscript for aluminum is 1 understood, so that means that my charge for ClO3 is ClO3-. We should be able to recognize that Al3+ is the formula for the aluminum cation, and ClO3- is the formula for the chlorate ion, so that makes the name of my compound aluminum chlorate. Now, let's take a look at calcium sulfate. Now, at first glance, it might look like our charges for our ions are just 1+ and 1- because we don't see subscripts, but again, recall that calcium is in group 2 of the periodic table, which means it has 2 valence electrons. It wants to lose those 2 valence electrons to get to a stable valence electron configuration of 8 valence electrons. And so because of that, calcium usually forms a 2+ cation. What that means is, since I don't see subscripts here, that means that a factor of 2 had to have canceled out, and that means the charge for SO4 would be 2-. So I should be able to recognize that the Ca2+ is the calcium cation, and SO4 2-, as we've already discussed earlier, would be the sulfate ion. So that makes the name of my compound calcium sulfate. So work on the follow-up assignment where you apply these same principles. If you have any questions, email. Again, we'll speak in class next time, and I will see you guys then. All right, have a good night.